So thanks, folks, for attending. We're going to talk about understanding and using impact so you know what vulnerabilities to fix first, aka using AI language models for cybersecurity like a pro, without the hype. All right? We're going to use these things for real. So I'm Chris from Yahoo Paranoid's product security team, and I need your help. I have a security hypothesis, the real reason I'm here. I want to prove it. I need a smart, friendly audience to help me. Show of hands. Are you an Ernie or a Bert? Ernie was the fun, irresponsible one, and Bert was the serious, responsible one. Who's a Bert? All right, I'd say about 70% of the audience. Who's an Ernie? All right, delusional. Thank you. We'll come back to that later. So, for this talk, another question. How many people are here to learn about state-of-the-art AI? Is that the primary interest in this talk? Versus impact. How many people were to talk about the impact and risk-based prioritization? Cool. And AI? AI state-of-the-art tools and how to use them? That's why I like B-Sides Dublin. It's a smart audience, doesn't buy into the hype. So we're going to cover both. Cool. I was worried it was all about AI, the interest, so we're covered. So, contributions to the industry. So, as part of this talk, I developed a taxonomy for impact, which we'll look at. A data set of all published CVEs to date, labeled by impact. So, if you're familiar with CVEs, they're the vulnerabilities associated with public, let's say, records, public open source, third-party software, and there's about 230,000 of those. So we've extracted the impact from those using AI, and I'll show you how we did that. And then a model that can determine the impact automatically from text description. So the data set is published on Hugging Face just recently. You'll see it there on the link. That's 230k CVEs with the impact extracted. Spoiler alert, this is not an accurate depiction of how it was done. So, risk is per asset and depends on the impact of a vulnerability being exploited by a threat. So, most people would have read that and thought, okay, I get it, makes sense. I didn't get that. I couldn't find a way that I could actually use that. So, my journey started with a presentation at B-Sides last year on the top left, basically understanding the building blocks, and subsequently going deep, releasing a guide in March with some of the thought leaders in the industry. And today on the talk, we're going to talk about impact. And ultimately, it was trying to understand impact, but also me trying to understand, for real, AI and LLM, how I can use them as a practitioner. And later on in the afternoon, we'll talk about EPSS. So, user need. So from LinkedIn, somebody posted, is there a machine-readable version of the technical impact of a vulnerability? And they give examples. And short answer is, there isn't. Which is strange because, as a user, that's probably the thing I care most about. In general and in cybersecurity, what's the impact to me? There isn't a taxonomy. Another user's view is, they were trying to understand in their organization a word cloud for their impacts. There is no machine-readable version of that. So that's what we're going to do. So the pitch. Our industry relies heavily on accurate, timely CVE information, and CVEs today are manually enriched. And the enrichment data is not as useful as it could be or should be. So we can prioritize vulnerabilities by exploitation, and that's a lot of what my talk in the afternoon will be about, and that's basically what CISA and Gartner recommend. Separately, we can prioritize by impact, and that's what we're going to cover here. And in order to facilitate that, we're going to provide a data set with the impacts extracted. Okay? Are you in? Would you invest? Show of hands. Woo. I'll talk to you later. So, vulnerability landscape. Quick overview. So, we have CWEs, which are weaknesses. The root mistake can lead to a vulnerability tracked by a common vulnerability enumeration, which can be exploited by an attacker, and there's a taxonomy CAPIC. common attack patterns, which can lead to an impact. And we're going to focus on the impact. All right, so that's just a high-level view of how all this fits together. Quiz. Cross-site scripting is a weakness, attack pattern, or impact. So shout out the answer altogether. Cross-site scripting is a... Oh, come on. Shout it out. Nobody can see you. You're on YouTube. They're going to see the back of your head. Cross-site scripting is a... Ooh. I'm not getting a chorus of answers. I'm getting a cacophony of different words. Let's try the other one. Remote code execution is a... Denial of service is a... Okay. So, cross-site scripting is an attack pattern. There's the CAPIC. There is a weakness associated with it, but it's a weakness associated with the actual weakness is the improper neutralization, which results in cross-site scripting. RCE is an impact, and denial of service is an impact. Okay, let's look at some examples. And we're just going to breeze through these, noting the red part, the impacts, and the CWEs. Just some examples: log4shell, Spring Shell, another example. You'll see that the weakness doesn't always relate to the impact, and that's why we need a separate impact. I like this one because there's a lot happening. It's got multiple impacts. And again, the weakness doesn't really relate to that. I'll tell you much about it. So if we look at SysAkev, SysAkev is the most relevant set of vulnerabilities. It's the known exploited vulnerabilities. And of that set, there's about 1,100. There's a subset which is the most exploited of the exploited vulnerabilities. And they release reports with international security agencies. And the info that they choose to report is, yeah, they report the CVE, CWE, but then they also have this thing called type, which is ultimately impact as well. Okay? So let's look at existing definition and impacts. And again, it's just looking at what's out there. So CVSS is what's used in our industry standard, our industry for prioritizing and scoring vulnerabilities. And it uses confidentiality, integrity, availability. The problem is, most of the stuff is high. So you can't really use the prioritize, because if everything is high, then nothing is high. Microsoft, for their vulnerabilities, they use different labels, and they relate to stride. And there's an example, whether it's elevation privilege, etc. So it's similar to some of the things we saw actually in the highlighted text, the red text from the CVEs, but unrelated to confidentiality, integrity, availability. CVE details provides metadata on CVEs. Again, we see on the right impact types. There's 5. They're kind of similar to what Microsoft gives, different. And then have these other types again. Again, it's just looking at what's out there. The main point is similar but different, not standard. So NIST vulnerability ontology, they talk about impact and impact type, and our impact method. And the main difference is the impact method is the means to an end, and the impact is the actual, reading data, writing data that we're most worried about. Again, there's a research paper summarizing vulnerabilities. They give a similar but different list. So there's lots of similar but different ways to represent impact. So let's look at MITRE. So MITRE are the folks that publish the CWEs and CAPIC, so they know what they're talking about. And basically what they're saying is, hey, look, there's thousands of CWEs, weaknesses, but there's only 8 impacts. So why don't we focus on those? Well, that sounds like a great idea, yeah? Why not? Well, the problem is there's no data. Where do you get the data? There's no, as we saw, standard identifier for the data. So while it's a good idea, it's hard to implement because there isn't a standard taxonomy. What they do have, if you look at a CWE, in there are these common consequences, and they list out technical impacts of different types. So, example for CWE 917 associated with log4shell, the technical impact was, example, read application data in terms of impacting confidentiality. So, there are some technical impacts buried in the CWEs, and a CWE can be associated with one or more CVEs, vulnerabilities. So, the data is not directly in the vulnerability. But if we were to look at CAPIC, within the spec, it lists out these on the bottom left, technical impacts, and if we were to map those, extract all the data from the CWEs and associate them with their scope, we get this heat map or matrix. So we can see, for example, bypass protection mechanism is primarily associated with access control. We can see that read application data, about midway down, is primarily associated with confidentiality, and so on and so forth. So taking that then, what we can do, we can create a taxonomy. And it looks as simple as this. So we split it out between logical impact and impact method. The impact, as we saw from NIST ontology, is the end result, and the method is how that's achieved. And the main things we care about are reading or application data, or modifying it, or denial of service of or application. And then there's various methods to achieve that, like remote code execution, etc., or bypassing access controls. So that's a very simple taxonomy. And if we take our example where we had a lot happening, the reds are the impacts, and we can map those to the taxonomy. So they map. So whether it's bypass protection mechanism, maps to bypass protection mechanism. Okay, so now we're getting a clearer picture. And so from the CV description, we can extract out the impacts, and they do map to our taxonomy, which is good. And looking at all the different standards that we showed, whether it was CVSS, Microsoft, CVE details, all we're showing here is they all fit under this impact taxonomy, which is good. So they're all different, they call them different things, but ultimately they can all map to this taxonomy. Drilling down, we can apply the CWE and CAPIC entries. There's IDs for each of these. So whether it's, example, cross-site scripting, it rolls up to code injection, which rolls up to unauthorized code command, which rolls up to execution. So we can take all of the CWEs and the CAPICs and map them to our taxonomy as well. So that's good, because there's, over 1,000 CWEs, and there's, approximately 500 CAPICs. And they do fit under this impact taxonomy. Moreover, within the CVE schema, there's support for impact, but it's not really used. We see it there midway down, and in the example that they provide, they actually use the attack ID, CAPIC, which is a bit strange. An attack pattern being used as an impact, so most impacts can be represented by an attack pattern, but we saw things like remote code execution that can't be. So either way, there's a place within CVE for impacts, if we can extract them. Okay, so that's all cool. We have a taxonomy, but we've got 230k published CVEs. How does our taxonomy fit with reality? So what we want, we are going to build a model that can automatically extract this information, these technical impacts, because there isn't a machine-readable version of these, and we do want them. And the problem type is multi-label classification. In other words, a vulnerability CVE can have one or more impacts, as we saw just here. There's 5. So multi-labels. Class imbalance, meaning that some vulnerabilities, example, denial of service, shows up a whole lot more than SSRF, as an example. It's unstructured text. It's, people writing text with typos and errors and all that. And it's a domain-specific language, cybersecurity, which is very, very different than medicine or horticulture, as an example. The constraints, we've no labeled dataset. We're doing this for the first time. So normally when you look at ML, tutorials, it starts with download the dataset. Problem here is we don't have one. Limited human time. This was done as a background task to the guide, which I published in March with other folks, which is a background task to my real job. And limited GPU budget, 50 euros or dollars. In contrast, the budget to train GPT-4 was $100 million. So the challenge, we have these 230k published CVEs. That's about 10 million words. 66 million characters, and the longest description is like 4k characters. So who's with me? Show of hands. Okay, under your seats, you'll find 20 sheets of paper with 50 CVEs. If you can start labeling now, you got 20 minutes. No, we won't be doing that. So, we're going to start by learning ML AI and finish with a conference presentation. That's how we do it. And the approach is, so understanding the problem, what we're trying to do, small verifiable steps, and automate as much as possible. Simple as that. And this is pretty much lean agile, okay, approach to things. It isn't a waterfall model. It's very much unstructured. As we do one thing, we learn, and we go back and we learn some more. So, does reality fit with our taxonomy? So, the traditional workhorse for natural language processing is SPACY, and this is typically what it would look like. And the normal method would be phrase matching, regex, or fuzzy matching. Okay? There are integration with language models as well. But we're going to use machine learning, and we're going to call a friend. And that friend is on Hugging Face. And so with Hugging Face, we can invoke models through our browser. So looking at the URL at the bottom, SecBert, we can invoke a model through our browser to, example, guess the masked word. And that's relevant because BERT models are trained using masked language modeling and next sentence prediction. That's ultimately how they're trained. And we can use it to extract the entities, whether it's attack patterns, etc., and impacts. That's named entity recognition. There's different models for different things. So we're going to rely here on the smart audience in front of me. So for the first one, what's the blank? Think about it. I'll say when, and I want everyone to shout out what's the missing blank for the first one. 1, 2, 3, shout. Second one. Out of bounds access. Any others? Any other takers? What about memory? I think we're in trouble, folks. Okay, let's ask some of Bert's friends. So we can look at non-security language models. Again, this is what we would get if we just used our browser. And we can see that these language models are not so sure. Their confidence is not so high. They select different words, but the confidence is generally low. So they're not cybersecurity trained, so they don't give good answers. If we look at security models, and I picked a few, code, the audience said code, so let's assume it's code is the right answer, the first one. And the second one, there's a mix. I deliberately picked one that's ambiguous. Could be read, could be write. Folks said memory, access. These models, yep, they came up with access as well, and memory, there you go. So these are the right answers. So the models can guess the blank word much better if they're trained in cybersecurity. That's the key takeaway here. The other key takeaway related to my opening question, are you an early or a BERT? I detected a bias in generative models. You'll note smiling, not smiling. Okay, so let's meet Bert's friends. So these are different capabilities that we have with machine learning. We have embeddings, which are basically numeric representation of words. We can compare those numbers to see how similar words or sentences are. We have topic modeling, which allows us to get a good understanding of what data is there. And when we're looking at 230K CVs, we want to get a good understanding of what is actually in the descriptions. Named entity recognition, we saw an example. We want to extract out certain things like impacts. Then we want to create a bootstrap classifier, as in something to help us classify the impacts, and then we want to improve that. And once we do all that, we unlock the next level, which is ultimately where we want to get to, a full-scale model that can automatically extract out the impacts and classify them. So we've got to level up, unlock on that one. And shown is a very high-level view of precision versus recall. Precision being how many of the retrieved items are relevant versus recall, how many relevant items are retrieved. And that's important. There's no perfect tool. And it's always a trade-off between those two things for any tool. So why BERT embeddings? Well, we saw earlier that security models, perform a whole lot better with security. So similar with embeddings, numerical representations of words. They have, let's say, that cybersecurity context. So any of the models that we use, we're going to use words or numbers with cybersecurity embeddings. And there's one already, AttackBert, available on Hugging Face, so we're going to use that. Somebody's built that already. And what that looks like is when we look at example set of CVEs, we see the different things mapped out into two-dimensional space. These vector embeddings are like 500, 700 dimensions, which humans struggle to understand, but mapped to two-dimensional space, it's a lot easier. And so we can see related things like on the right we have path traversal and directory traversal are very close together. And so that's basically, there's a semantic understanding of how things relate based on the embeddings. So let's look at topic modeling. So when we're approaching a data set for the first time, we understand what's in it, what are the topics. And, 230k CVs is a lot of text to try and understand. And topic modeling allows us to do that. And it's unsupervised, meaning you give it a chunk of text and it figures out what's the relevant topics or things. So via diagram, you give it an unsorted list and, without any pre-processing of the data, it clusters them based on their semantic similarity, which is great when you're trying to figure out, well, what is in this massive data set? It's very simple. These are the main lines of code. As I said, we're trying to understand these things so we can use them, and this is how you use them. We use AttackBert for our cybersecurity embeddings, and we just call BERT topic for the topic modeling. Very simple, a few lines of code. Most of the things I talk about here can be done in less than 10 lines of code. Okay? They do things like clustering, so it understands things are related. Like at the bottom, we see that Stack Overflow and Heap Overflow ultimately chain up to buffer overflow, so we could collapse those things together. And it's important to understand that we didn't tell the model anything, we just gave it a chunk of all the CVEs and said, go figure out the hierarchies and topics for me. Completely unsupervised, which fits with our limited time and budget. It does things like word clouds, which is pretty standard, but it as I say, from taking all those descriptions, you can create the word clouds for you. An example of a user need, I work with Jay in EPSS, Special Interest Group. Jay was trying to understand, there's a relatively new CWE dataset called 1400 because it has 1400 entries, and they're massively complex. There's a lot of dependencies and relationships between them, very hard to understand. So I said, hey, I've looked at this and I'd recommend topic modeling. So I took the CSV file of 1400 entries and ran the topic model. And what it shows is that on the right is the, let's say, categories that come with the 1400 view, but the topic model was able to figure those out. I overlaid the bold black text from the categories on the right, and you'll see they're very similar. So again, we took a file, did nothing with it, gave it to the model and said, go figure this out. What's the relevant info, grouping it together. And that's the beauty of topic modeling. Okay? And the value isn't that the headings were the same, it's more that you can interact, you can zoom in and interact and see related things. So get a very good understanding. So now, we can't really talk about AI without talking about ChatGPT, so I'll talk briefly about this. Different things we can do with a LLM. We can use it in a zero-shot fashion, as in ask it questions. We can create synthetic data, we can label data, and we can validate label data. So let's look at a few examples. So here, I've prompted GPT-4 saying, hey, here's an example of a vulnerability, here's the labels that are available, tell me with a probability which ones you think it is. So when people talk about language models, they talk about hallucinations. Most people don't understand that models know how confident they are by design. So if you ask the model, hey, how confident are you with the answer, that will largely reduce the hallucinations. In other words, you know how confident it is, it'll tell you. So here we can ask, how confident are you with the answers? Okay, so that's cool. It's classified. The last command injection wasn't so sure about. So here we ask GPT to now create a prompt. So we say, create a prompt with a few examples to be fed to an AI. So we're not asking it to classify something, we're saying, create a prompt to classify something for an AI. And it does. And then we take that prompt and we feed it back into ChatGPT and it performs better, as in now it's more certain that command injection is 0, as an example. And all we did was ask the model to create a prompt and give it back to it. So we gave it a few examples and it learned, in-context learning. We can validate labeled datasets. So the struggle, as I said at the start, is there isn't a labeled dataset. I looked around. There was one from 2018, 3 language models. and I said, hey, please validate this data set for me. I took copy-pasted some examples and said, tell me how confident you are and whether you agree or disagree. And then I just skipped the whole file of 500 entries and said, right, tell me which ones you disagree with. And we see the first one, it's correct. The others, it made a good point. But of those 500, it came back with 5. That's pretty good. And it found an error. And this is training data, as in, this is the data that was used to train the model back in 2018, so it's very important. And within minutes, the GPT can detect errors. So let's look at named entity recognition. This is where we saw that we can use a model to pull out the things we're interested in. And this could be, song, title, artist. It could be anything, any genre or topic or field. And they do exist in Hugging Face for cybersecurity. So an example on the bottom left, we can see we give it a vulnerability description, and we say, hey, it's trained to actually only pull out vulnerability, the observed data, and attack pattern. So the model, that's all it does and understands. Okay, it's fixed, and that's all it can do. Again, you see 10 lines of code, how we invoke it, and this is similar to invoke it via the browser. And it comes back with, what it thinks is threat actor attack pattern. So named entity recognition. Useful. And this could be, as I say, any entities at all, cybersecurity or not, depending on what we're trying to do. There's models for everything. So NER is cool. So what I found, though, was that the content that came back from that previous cybersecurity model wasn't great. It was too verbose. I wanted something short and sweet and succinct. And I came across GLiNER, and originally I started playing with it. It was the medium version, and it was kind of one of many things I tried. It was kind of like, meh, not really doing it. And then I tried the large model, and I was blown away. It's like, whoa, what magic is this? It was able to extract out the impacts just like this. So give it some text, give it the labels I wanted to extract. And this is a general purpose, meaning if I give it something content about music, it could, and I told it pick out the song, music, whatever artist, it could do that. So it's general purpose named entity recognition. I could tell it pick out whatever from whatever text. So it's general purpose, state of the art. It's pretty cool. And I was, as I say, blown away by this. What magic is this? I thought to myself. And it's only 10 lines of code again. So super powerful. And yeah, this was one of the workhorses for what I wanted to do. The other code was wrapping this up, feeding it 230k CVEs, processing in 1k chunks, and that was the code. You're talking about 20 lines of code. There was a bit more to it than that, but this is the workhorse. So this is kind of what we get. Given a CV description, it pulls out the things I want, SQL injection, SSRF, etc. That's pretty cool. Again, I emphasize general purpose, no pre-training, not trained on cybersecurity specifically. One of the 11 data sets is programming related, and it outperforms the older cybersecurity named entity recognition tools. Super powerful tool, super easy to use. And so overall, and I know I'm mixing my Muppet metaphors here, sorry about that. The Swedish Chef is one of my favorite characters in my youth. But how we do all this then, the recipe is this. Using GLiNER to extract out the impacts, and then spacey NER to augment that. In some cases where it says denial of service, it normally has brackets, whatever, crash or memory consumption, whatever. I wanted that part in brackets as well. And that's really it. Then per topic, we can use the topic model and remove the outliers. Okay? So using the tools that I just described in, functionally, you're talking about 10 lines of code for each one, is the core code. That's how you get to extract out the impacts from 230,000 CVEs. Simple as that. So some of the interesting things it found. There's some mad stuff when you look at what's in CV descriptions. Everything from foreign languages. The first one suddenly switches to German for whatever reason. You get typos. You get things I didn't know. I didn't know hair hunting was a thing. It is. Android specific. But it's able to extract out things that, if you were using regex or traditional technology where you have to know what you're looking for, this pulls out new things. In other words, it can support concept drift. New concepts, it can extract them out. which is pretty cool. And so we have ones related to, the last one is related to cryptocurrency, where there's financial damage. Ultimately it's just software, and in this case it's currency and financial damage. So if we look at the distribution, we see that there's a relatively small set. If we look at the top 100 key phrases, the things that came out, they account for about 50% of everything in the CVEs. So you get this Pareto type distribution. Some things that were not extracted, because sometimes there's nothing to extract, are very hard to understand, what's the problem. Where you get things like the first one, what's the impact? Well, it doesn't say. Nothing to extract. And so you get a lot of those. So I'm going through those at the moment, figuring out, and even let's say the second last one, people may struggle to understand what is the impact there, what's the problem. Passwords were hashed chat256. What's wrong with that? Okay, so let's look at SetFit then. So we have now extracted out the impacts from our CVE data, and we want to be able to classify them. We don't have that much data, and we want to build an AI model to assist us in labeling the data. So we can use SetFit. So what's SetFit? So SetFit is good at few-shot learning. It excels when you have limited data. So here we're going to use it with our limited data to go from, we went from kind of no data to extracting out the impacts, and now we need to label them. We can use this model because it works well with limited data as a classifier, kind of like as a bootstrap classifier before we get onto our bigger classifier. And even if we ask ChatGPT which is better for our, purpose, ChatGPT will tell us for this specific purpose, few-shot learning, limited examples, SetFit will generally outperform it. People have this thing that bigger models work better. That's not the case. BERT excels because it's bidirectional. It gets context and meaning from words because it understands words before and after. That's the bidirectional bit. Versus GPTs. So, kind of some simple metrics or differences. It'll work well with 8 labeled examples. So example, if we said denial of service, I had 8 different examples, I could train a model with 8. So it's 8 versus example 800. That's a big difference. Again, the code, 10 lines of code, and you can train the model in, seconds rather than hours. Again, you go from nothing to something with minimal code and time, and we now have a bootstrap classifier that can help us an AI assistant, if you like, for classification. So Ligon is a recent addition, came in January, and that generally just improves performance, not by changing the model, but by using the text input. It's very clever how it does that. I won't go into details, but it basically, how SetFit and Ligon work is that there's information by knowing that a given description is a class. The information is also that it's not in this other class. So you get this contrastive, and you can compare things and work out the difference. So you're basically learning by the difference of things, not just the thing itself. So this is pretty cool. And it extends how many samples and the benefit of SetFit. SetFit is typically limited to about 50 examples. In other words, it either stops improving or deteriorates if you have too many samples, which is unlike bigger models. So the BERT model implementation this is all now, once we have a labeled data set, this is all standard tutorial stuff, all right? Not much to say here. We ultimately want to build a model for classifying and extracting out, as in named entity recognition, extracting out the impacts. And as I said, standard tutorial stuff at this point. The only hard problem is dealing with the class imbalance, and that's a standard textbook thing as well. So as we said, some of the impacts, like denial of service and RCE, will feature a whole lot more than SSRF, as an example. And that does impact how we train the model if we want to get good results. Again, all standard textbook stuff at this point. And the reason we're using a bigger model is it can work better with more data and give more context. So it's only at the very end, once we've kind of started with no data, use topic modeling to understand, well, what is in all this data, using named entity recognition GLiNER to extract out the impacts, using SetFit then to start with limited sample of data to classify them, and then build up our classified data set. Now we have a data set that's classified, and we can actually train a model. We've solved the hard problem. Where's the labeled data set? And then we're into standard textbook stuff at this point. So, to recap our journey, we looked around at what was out there for impact, and MITRE says, hey, why don't you use impact to prioritize? Which is great, but there's no standard taxonomy, and there's no machine-readable version of the impact. So we've heavily relied on what's in MITRE CWEs to build our taxonomy, and it's very simple. And we saw that we can map other taxonomies to that, and CWEs and CAPEX. That's pretty cool. And then we validated that taxonomy against reality. We showed example where cross-site scripting would roll up in terms of CWEs and CAPEX up to that. And in general, all of those, hundreds or thousands of CWEs and CAPEX can roll up to our taxonomy, which is pretty cool. And as I said, the descriptions do include the impact, whether it's RCE or denial of service or whatever, but there's no machine-readable version of those. We looked at Bert's friends to help us, and BERT was the standard technology that we used, and we used it in different ways, from trying to understand the data to classifying the data to building our final models. So the takeaways. The hypothesis, going back to the opening point, was that security people tend to be more Berts than Ernies, right? And I think we're there on that one. We can conclude satisfactorily with the numbers, yes. I'm an introvert Bert myself, so yeah, don't feel too bad. Okay, so the other takeaways. Enriched vulnerability data on impact and exploitation allows for effective granular risk-based prioritization. With 230k published CVEs, with approximately 100 new CVEs being published every day, it's very hard to keep on top of those, and we need to prioritize. In the talk later on, I'll talk about how we can prioritize by exploitation. 5% of CVs approximately are exploited. Let's prioritize those. And now we talk about impact. So it's a separate independent prioritization method. So the key secret, I think, to get on top of all these CVEs is risk-based prioritization. And here we showed how to do it with impact. So the first steps to doing all this is, one, define a taxonomy. Like, what is the taxonomy? That machine-readable format that humans can understand, okay? There shouldn't be 1,400 things. It should be easy for humans to understand, like we showed, 8 or 10 for our taxonomy. And we can roll things up to that. And also make it easy and automated to extract this information. We can encourage people, say, hey, you should, put impact in your CVEs, but that's great, but unless we make it easy, people won't, naturally. So let's make it easy and automatic to do that. Extract that info and get it into the CVEs. Okay, and to the gentleman who was asking about AI and all the hype, did you find value in any of this? How much of this was hype, and how much of this do you think was useful? Yeah. So good points. False positives, basically. So that's why we use traditional methods, and we can count. If there's one of a data set of 200k and one comes out and doesn't fit with all the others, it's probably an outlier. Okay, and that's how we can deal with false positives in the context of all the data. But that's why, yeah, as I said, ultimately all this is about balancing the precision and recall. There's no perfect solution. Okay, so LLM tools are very powerful. They will be used a lot more, and especially in cybersecurity. So thank you to all the folks who've given me 40 minutes of your lives, to the folks who built the tools, to Yahoo for cultivating such a rich environment for people to thrive and putting people first, and for B-Sides, Nadine and crew for making this happen. B-Sides is my favorite conference that I don't choose to talk at many conferences. This is the one I choose to talk at because you guys. So thank you all. Do we have time for questions? 5 minutes for questions, folks. Is there a mic or can you shout? You might have to shout.
So for a new vulnerability, if one was announced today, would your models be able to help predict if there would ultimately become a non-exploited vulnerability?
So no, that's where EPSS, that's its purpose. And we'll talk about EPSS in the afternoon. The exploit prediction scoring system. It gives a probability between 0 and 1 to say, here's the probability that this new vulnerability will be exploited. Once that vulnerability is assigned to CVE, it can then predict the probability. So that's what I'll talk about in the afternoon. Yep.
In terms of impact, have you ever considered using Yahoo's data set of benefit submissions that have price tags and actual working backwards and inflating vulnerability?
So yes, I considered it. We don't, let's say, haven't done it because this is kind of where we are. But my viewpoint is our whole DevSecOps pipeline end to end, right through to bug bounty, and how to relate those things together. So yes, my mental model is all the stages of the DevSecOps pipeline and how they can be used to inform each other. So let's say for exploitation, we use bug bounty. If something shows up in our bug bounty or incident response, we prioritize that as exploitation. So yes, we've considered it. No, we haven't done it because we're not there yet. But absolutely, yes. We will do the correlations against payouts and impacts and see if there's correlation and if there's value in that. But absolutely, yes. One of the things we've achieved as well is getting all our data into a data lake so we can actually do this type of things and just let the machines figure out the associations and how we might benefit from them. But yeah, that's a really important point that all of this is in an overall context, and trying to inform that context with the different tools is important. We're trying to, like Yahoo delivers value to our customers through software, through our DevOps pipeline, and that's what all this is about ultimately. Yes. So we had different versions of this. This started off as a simple regex a few years ago. We wanted to figure out RCEs and memory buffer overflows. And then, I guess 2-3 years ago, I built a non-LLM model. So it was better and it pulled out stuff. So it allows us, so it wasn't on many classes of things, as I say, RCEs and memory buffer overflows. So we use that in production. We are now that we have, let's say, more classes and more impacts, we're trying to figure out, well, how can we use those in bug bounty? How can we use those in wherever? And then we see, well, what's coming in terms of public CVEs? Is it, and that's what we do, example, with our bug bounty. What are the things coming in? Is it cross-site scripting? Is it whatever? All those things, putting it together. So we basically, expand out the capability. That's been there for years in a much smaller scale. One more question? Say again? Yeah, so has the large language model made it easier for upper management in terms of cost and risk? I would say no, not yet. That's where exploitation is a whole lot more, it's an easier sell because 5% of CVEs are exploited, and we can say, well, if we only fix, or let's say if we prioritize those first, we can save this amount of money. That's a much easier sell. With impact, because there's a lot more things, it's much harder to, let's say, get the granularity for prioritization. So I haven't put together the business case for impact yet. The business case for exploitation is there already. That's an easier sell. So with all these things, when you build something, you need to see how it plays out in your reality first. And, so yeah. All right, folks, much appreciated. Thank you very much for your time.